Far and away, the most common distribution that is used across probability and statistics is the normal distribution. The normal distribution is so common that it comes up just in colloquial speech. We will often refer to it as a bell curve rather than a normal distribution, but it arises all over the place. And some of this is because it's a mathematically convenient distribution, and some of this is because there are many quantities in the real world that actually are approximately normally distributed. And so, as a distribution, it is probably the most important one to learn about and to become familiar with. So the most common distribution in all of probability and statistics is, without a doubt, the normal distribution. Right? It's the bell curve shape. So if you're thinking of a bell curve, you're thinking of the normal distribution, and it arises very frequently. So what is the normal distribution? Well, we'll take x to be a continuous random variable, and we'll think about x as following a bell curve shape. Then the distribution of x is referred to as the normal distribution. Every normal distribution is parameterized or characterized by two parameters. These are going to be mu and sigma squared, and mu and sigma squared represent both the mean and the variance of x, respectively. So the expected value of x is mu, the variance of x is sigma squared. What we do is we write x follows a normal distribution. We use just n to characterize the normal distribution, and it has a density function given by f of x, which is 1 over the square root of 2 pi times the standard deviation times e to the power of x minus mu squared over 2 times the variance. Okay? The CDF of x is actually not available in closed form. So there is no closed form expression for the CDF of x, which is going to be a trouble to using the CDF. However, we can use computers or similar software to calculate the CDF for us. The normal distribution is going to characterize quantities that are symmetric around the mean with a fairly tight clustering around that value. And so we see that the symmetry of the normal distribution is such that being above or below the mean within a fairly tight range is what we're most likely to observe. And there's going to be this symmetric pattern around it. So it's quite unlikely that we're going to observe any value that is very far from the mean. So why do we think about the normal distribution so much? Well, there's a ton of real-world applications that are going to show up as being approximately normally distributed. So many quantities in the real world act as though they're approximately normal. In order for them to be truly normal, it must be possible to observe any value between negative infinity and positive infinity. The normal distribution is defined across the entire real line. However, if we ignore the firm normality and we just think about approximate normality, then many quantities start to fit the picture better. So because we have that concentration around the mean, in practice, being defined on the real line is not that important. So for examples, the grades in a classroom are oftentimes going to be approximately normally distributed, right? If you think about a professor that is grading to the curve, they're grading to a bell curve. That bell curve is the normal distribution. The heights of humans are going to be approximately normally distributed, right? So most humans are around average height. There's many of them are quite close to being average. There's very few that are far from average height. Right? Birth weights in infants. So the, again, average birth weight of most infants is going to be quite similar. You're going to have some that are a little ways away, above or below, right? Fairly symmetric pattern there. You're not really going to have any infants that are very far from average. If you look at the errors in measurements within lab sciences or within physical sciences, those measurements that you're taking, because you use instruments that are not sort of perfectly precise, you're going to have errors in those measurements. Those errors are going to be approximately normally distributed. So again, typically it's going to be fairly small, close to zero, right? You're going to have some that are too high, some that are too low, but you're not going to have huge errors typically. If you look at protein content in milk, say from cows, that is going to be approximately normal, right? The satisfaction of jobs is going to be approximately normal. If you look at blood pressures and you transform them accordingly, you're going to have approximate normality. The returns of stocks are going to be approximately normal. So we have all of these quantities, right? You could come up with tons more that are going to be approximately normal. And what they all share is that they all sit close to the mean, right? Very few points are going to be far from the mean. Very few observations are going to be very far from the mean. But we also have this symmetry pattern. And so if we start trying to visualize what the normal density looks like, we see this bell curve here, right? So this characteristic value of our bell curve Okay, and so we're starting with a normal with a mean of 0 and a variance of 1, right? And so the bell curve is going to be centered on this value of 0. We're going to have symmetry, right? So the positive and the negative section look exactly the same. And what we can see is that almost all of the values are going to fall, say, between -3 and +3, right? So if I just measure out where about -3 should be is something like this, for instance, right? And then +3 is going to be up here on this side. And the density outside of this interval, right, is going to be basically 0. Right, we see that it's essentially down here at 0. It's slightly positive, right? We never quite get to 0, but it's going to be basically 0, okay? And so then almost all of our density is falling sort of in this region between -3 and +3, right? And so as a result, we have this symmetric clustering tightly around 0. And so then we can start to ask, well, what happens if we change the different parameters? And so first we'll change the variance, right? If we lower the variance, right, we make less variable, then what we see is that that point, the probability that we're around 0 is going to be increasing. We increase the density around 0, and we make everything tighter, right? So we're actually pulling everything in. It's now even not common to get out to -3 and +3, right? We're instead going to be clustered, let's say, around -1 and +1. We still have a symmetric distribution, and so the variance does not change that symmetry, but we can see everything is sort of more tightly clustered. If instead we were to increase the variance, then you can see that point in the middle is actually lowering, right? And if we say go up all the way to 4, we're getting a less tightened bell curve. And so then there's sort of this expansion out where now we're up to, say, around 5 and -5, right? And so as we move the variance, if the variance is lower, things are more tightly clustered around the mean. As the variance gets higher, you have a flatter bell curve. It's still a symmetric bell curve shape, but it's flatter, and there's going to be more variability. You're going to be more spread out. Right? So if we set this back to be 1 here, right, then we can look at what happens if we change the mean. Right? So if we increase the mean, what we see is that the bell curve actually just shifts around. So the center of the bell curve is always going to be wherever we set the mean. Right? If we set it at 2 here, right, then the bell curve is now centered at 2, okay? And so we end up with the same shape, except just moving up or down, right? If we bring it down, then it could be at, say, -5, and the values are not going to be any more or less spread out. We're just moving where the location of it is, right? And so in this case, we can actually think about any bell curve shape that we would like, right, where we can dial in both the mean and the variance. All of these are just going to be bell curves, right? Either sort of very flat or very steep bell curves located wherever we want them to be located. But we always have this symmetry around the mean, and we're always seeing that most of the values are going to be fairly tightly clustered around the mean, where how clustered they are is going to depend on the variance, right? So we still see, even with a fairly high variance, this trailing off happens fairly quickly, but in theory, there's always going to be this positive density of taking on any value that we might want. Okay, so that's the shape of the normal distribution, and that's how the two parameters are going to influence its specific shape. So how do we go about interpreting the normal distribution? Well, the two parameters mu and sigma squared represent the mean and the variance of the distribution directly. And as we just saw, the mean specifies the center of that distribution. And so it is the center of the point of symmetry. It's also the location at which we're putting that bell curve. Because we have symmetry, what we can say is that the probability that x is below its mean is always exactly 0.5. So there's a 50% chance that x falls below the mean. Changing the mean is going to shift that location of the bell curve, but we're still always going to be the case that there's 50% probability of being less than the mean. Now, the variance captures how dispersed the bell curve is, right? So higher values of sigma squared represent a wider and a flatter curve, right? Smaller values would represent a narrower and a higher curve. Most of the bell curve, what we're going to find, falls between plus and minus 3 standard deviations of the mean. So if you go mu minus 3 times sigma, and you go mu plus 3 times sigma, that's going to give most of the observation. Almost all of the probability is going to be between negative and plus 3 standard deviations. And we saw that when we were looking at the graphic of the normal 0, 1 distribution. In that case, we saw almost everything is falling between -3 and +3, which is exactly the mean, in that case 0, minus 3 times standard deviation, which would be 1, right? So between -3 and +3, almost everything is going to fall in that range. And that will always be true no matter the value of mu and sigma. Now, the symmetry of the normal distribution is even stronger than that, right? So what we can always say is that for any value of c, right, if you want to know, well, what's the probability that you are less than mu minus c, that has to be the same as the probability that you're greater than mu plus c, right? And so the probability that you fall into either of the tails of the distribution is going to be exactly the same. So being more than c units away from the mean is equally likely in both directions, right? And we can visualize this using sketches considering the area under the curve. And so sketching in the normal distribution is going to be a very common skill that you'll want to use all over the place. And so let's take a look at what this symmetry property actually seems like with sort of a filling in the graphic here. And so what we will do is we'll draw a really rough sketch of our bell curve here. It never needs to be sort of a perfect bell curve, right? Just to get the general idea here. And so what we know is that the mean of this has to be that center line, right? That's going to be the height of our bell curve here. And so what we're wanting to think about is, well, what happens with the probability that you are, say, mu minus c, and that you want x to be less than or equal to mu minus c here. And so the probability of any event within a continuous random variable is always going to be the area under the curve, the density curve that satisfies that event. And so in our case, this probability is going to be exactly this area down here. And so that's what this probability is. Now, the claim that we're making is that if you are then to consider the probability, for instance, that x is going to be greater than, say, mu plus c. So we come over here and we take this event mu plus c, right? And we want x to be greater than that, right? This is going to be the area under the curve up here. So it's all of that area there. And the claim is that these two quantities are exactly the same as one another, right? And this should make some sense if we think about this as being a perfectly symmetric curve, because if we sort of were to fold over one half on the other, right, and we think about folding these together like a book, then we're going to find that this area down here is exactly the same as this area over here, right? And so that's going to be true no matter what c is. And so in particular, right, if you want to know, well, what's the probability that you're less than the mean, that's going to be 50% right here, right? The other 50% is up here, reflecting that. Okay, and so anytime that we're dealing with our symmetric probabilities in the normal, we can always know that the upper tail and the lower tail are going to be the same probability, right? The point here, if you are c away, is going to be the same as the point here if you are c away. And so the distance from the mean, this distance right here, is really what matters in terms of determining those probabilities. Okay, and so that symmetry property is going to be a property that becomes very useful if ever you're trying to calculate probabilities relating to the normal distribution. So let's look at some examples from the normal distribution here. So suppose that final grades in a particular course are graded on a curve, so they follow a normal distribution. The mean score is 70 and the standard deviation is 8. Okay, so what is the approximate distribution of a randomly selected score? Okay, and we say approximate here because we're dealing with our approximate normality here. Okay, so we know that we're going to be dealing with a normal distribution, right? The normal distribution requires two parameters. It requires mean and the variance, right? So mu and sigma squared. And so what do we get here? Well, the mean is going to be 70, right? And the variance is the standard deviation squared. So that's 8 squared. And so that's going to be the normal 70, 64 distribution, right? So that's our approximate distribution for x here. Okay, so importantly, when we're writing this down, we have to remember that we characterize it using the variance. And so we were given the standard deviation here. We need to convert back to the variance. So what is the probability that a randomly selected student scores above 70, right? So what we want is the probability that x is greater than or equal to 70. So just noting that this is going to be the same as 1 minus the probability that x is less than or equal to 70. And if we think about our normal distribution, right, that's 1 minus the probability that x is less than or equal to the mean. But of course, when we are thinking about our random distribution here, right, our mean is always the center. And so the probability that you're less than this is going to be equal to 0.5 always. Right? Now, of course, we also saw that through symmetry, this 0.5 has to be the same as this 0.5 up here. Okay, and so we could have used that to work out the probability directly, but using this, we can say that has to be 0.5. Right? So the probability that a student scores less than or equal to, or scores above 70 is 0.5. Now, what is more likely, that a student scores below 60 or that a student scores above 80? So we want to know, is it more likely for the probability that a student scores less than or equal to 60 versus student scoring greater than or equal to 80? Now, note that the 60 here is going to be our 70 minus 10, right? So 70 being the mean in this case. And the 80 here is 70 plus 10. And so in this case, right, if we again sketch out what we're thinking about with our graphic here, we have our bell curve drawn in, right? Our mean is at 70 here. And so we want to go down here to 60, right? And so that's the 10, or we can go up here to 80. So that's again a distance of 10. And what we know is that this area on both ends has to be exactly the same, right? So this is the same. That area is exactly our probability. And as a result, the student scoring below 60 or student scoring above 80 have to have the same probability because of the symmetry of the normal distribution. So probability that x is less than or equal to 60 is the probability x being less than 10 below the mean. Probability x being greater than 80 is the probability that x is above 10 above the mean. And so they have to be the same probability there. Now, what's more likely, that a student scores below 50 or a student scores above 95? And so here, if we think about drawing out the same type of distribution pattern that we've been looking at here, right, we start with a 70 down here, and then we can go down 20 to the 50, okay? And so we'd be thinking about this probability down here, that highlighted region, or we can go up to the 95, and we'd be thinking about this region right here. Okay, and so we're asking, well, which of these regions is going to be larger? Now, importantly, right, we have 20 units that go between 50 and 70, and we have 25 units going between 70 and 95. And so what that means is that if instead we were just to consider these 20 units above, so that's going to be down to 90 over here, right? This whole area above 90 is going to be the same as the area over here, okay? But we're not considering that whole area above 90, right? We're considering the smaller area that is just above 95. So that area has to be smaller. And so what we're saying is that the probability that x is greater than or equal to 95 has to be smaller than the probability that x is less than or equal to 50. And that's because this area for 50 would be the same as the area above 90, but that area above 90 is smaller than the area above 95 is smaller than the area above 90. Okay, so what we're saying here is that it's more likely that a student scores below 50 than a student scoring above 95. So the probability that x is less than or equal to 50 is the probability that x is below mu minus 20. Probability that x is greater than or equal to 85, it should say 95 there, is mu plus 25, right? And so as a result, we have the probability that x being less than or equal to 50 must be higher, since it's equal to the probability that's greater than or equal to 90, but that is going to be an upper bound on the probability there. And so we can see that from the sketch, or we can work through algebraically to get to that response there. So the other reason that we really like the normal distribution is because it exhibits what we call closure properties. And so in mathematics, closure properties are when we do something to a mathematical object and its type does not change. And so the normal distribution has a few of these different properties. So to see these, let's suppose that x follows a normal distribution with a mean of mu and a variance of sigma squared. And then we take a and b to be both constants. What we can say is that if you take a times x plus b, this is also going to be a normal distribution where the mean is now a times the mean of x, so a times mu plus b, and the variance is a squared times the variance of x. So if you transform a normal variable through a linear transformation, it stays normal. This is not going to be the case with every distribution. This is a rare property of distributions, but it is a property of the normal distribution. So the other closure property that we can think about is, let's take y to be a normal distribution. Here we're going to say that its mean is mu2 and its variance is sigma 2 squared. And then suppose that we have a covariance between them, that is sigma x sub y. So then what we can say is, if we look at the sum of x and y, then that's going to have a normal distribution. The mean is going to be mu x plus mu y, and the variance is going to be the variances summed together, so sigma squared plus sigma 2 squared, plus 2 times their covariance. Okay, and so if you add multiple random variables, normal random variables together, you keep something being normally distributed. If x and y are independent, then they will have zero covariance, and so then that would simplify down to the means adding together and the variances adding together as well. If we take x1 up to xn as all being independently normal, following a normal distribution with mu I and a sigma I squared, then the total summation is also going to be equal to the normal distribution where you sum up the means and you sum up the variances, right? And again, there's no covariance because we're assuming that they're independent of one another, right? And so then in particular, if you take all of the means to be the same and you take all of the variances to be the same, then the sum of a group of normal variables is going to be normal with a mean of n times mu and a variance of n times sigma squared. This is a property that gets used very frequently when dealing with normally distributed random variables. If you assume that they're independent and identically distributed, they all follow the same normal distribution, they're all independent of one another, then you end up with the summation of normals simply being another normal distribution. And so this closure property becomes very helpful when you're manipulating normal random variables. So let's look at some examples here. All right, we'll take x to be a normal with a mean of 3 and a variance of 9, y to be a normal with a mean of -3 and a variance of 4, and z is a normal 0, 1. We're going to take the covariance between x and y to be -2, and then assume that x and y are both independent of z. So what is the distribution of 2x plus 3? Well, here we can use that first closure property of the normal, right? And 2x plus 3 is going to follow a normal distribution. The mean is going to be 2 times the mean of x, which is 3, plus what we add on, so that's 3. And the variance is going to be 2 squared times by the variance of x, which is 9. Right? So then if we work out that's 6 plus 3 is 9. Right? So that's a normal with a 9. And then 2 squared is 4 times 9 is 36. So 2x plus 3 has to be a normal 936 distribution there. Right? So multiplying through, we get 9 and 36 as the parameters of the normal. Now what about x plus z? So here we have the case that x plus z are going to have to follow a normal distribution, right? Because they're independent, we add their means and we add their variances. And so the mean of x is 3, the mean of z is 0, the variance of x is 9, the variance of z is 1, and so this is going to give us a normal 3, 10 distribution. Right? So it's still normal because they're both normal. We add their means, we add their variances because they're independent of each other. What about the distribution of y minus z? So what we can do here is we can rewrite y minus z to be the same thing as y plus the negative of z. Okay? And then if we think about, well, what is negative z? Negative z, because of the closure properties, has to be normal, where the mean is going to be -1 times by its mean, but that's just 0. And the variance is -1 squared times by its variance. And so this is just simply a normal 0, 1 random variable. And so as a result, we're going to have y plus a normal 0, 1 random variable, but it's independent of that random variable, right? And so then what we can get here is that y minus z is going to follow a normal, right? We take the mean of y, which is -3, plus the mean of negative z, which is 0, so we can just have that as -3. And then we have the variance of y, which is 4, plus the variance of negative z, which is 1, so that's 4 plus 1. And so then we're going to have a normal -3, 5 distribution. Okay, so walking through that once more here. Because negative z follows a normal 0, 1, so then y minus z has to be a normal with a -3 and then 4 plus 1, so a -3, 5 distribution. Now, what about the distribution of x plus 2y? So again, here we can work out, well, what's the distribution of 2y? Right, so 2y is going to be normal. You take 2 times by the mean of y, so that's going to give us a -6. You take 2 squared times the variance of y, so 2 squared is 4, multiplied by 4 is 16. Okay, and so that's the distribution of 2y here. Now, what about the covariance? So we want the covariance between x and 2y, but that's just simply 2 times the covariance between x and y, right? And so 2 times that covariance is going to give us a covariance of -4. And then we can plug in to our formula there, our closure formula. So the mean is going to be the mean of x plus the mean of 2y. The variance is going to be the variance of x plus the variance of y plus 2 times their covariance. So what can we do here? Well, we can say that 2y is going to be this -6, 16 normal distribution. The covariance is -4, and as a result, x plus 2y is going to be 3 plus -6 on the mean, so that gives us a mean of -3, and the variance is going to be 9 plus 16 plus 2 times -4, which gives us 17. And so x plus 2 times y is a normal -3, 17 distribution. So the normal distribution is going to be an incredibly important distribution. It is the most commonly used distribution across all of probability and statistics. It's characterized by its mean and its variance, and it makes up this bell curve shape. The mean shifts where that bell curve is. The variance talks about how flat or how steep it is. It's going to be very useful mathematically because of its symmetry properties, because of its closure properties. It will come up sort of all over the place. And the main dilemma that we have with the normal distribution is that if we want to calculate probabilities, we don't have a closed form version of the CDF for the normal. And as a result, we'll need to build up some extra tools in order to calculate probabilities relating to the normal distribution. But outside of that lack of a closed form CDF, the normal is incredibly useful mathematically, and it comes up all over the place with real-world quantities, which justifies its prevalent use across probability and statistics.